A circular plate of metal is heated. And the heat causes it to expand at a rate of actually causes its radius to expand at a rate of 0.01 centimeters per minute. And then I think part of the question got cut off, but I'm fairly certain the question must be, at what rate is the area increasing? Wow, writing is really good. When the radius is 50 centimeters. Okay, stuff stopped converting, finally. All right, so this is the second. And again, maybe not again, related rates, I kind of have a 4-step process I like to use. First step, what's changing? So in this case, the things that are changing are the area and the radius. So area, that's what we want to know how it's changing. And I typically like to use the Leibniz notation. You're welcome to use other notation, but I'm going to write that as dA dt. Right? We're asking how area is changing as time is changing. We don't know that. What we do know is how the radius is changing. We know the radius is changing, so we know that dr dt, the rate of change of the radius, is equal to, it's written somewhere in the problem, 0.01 centimeters per minute. Wow. Writing today is just a challenge, apparently. Okay. To me, well, I should say, drawing a picture is often the first step, but after drawing a picture, if a picture makes sense to draw, this is kind of our first step. Figure out what's changing. And then the second thing is is to relate how those things are changing, meaning that's kind of not the right way. I want to find an equation relating the variables. In this case, that equation is going to be area equal to pi r squared. Yeah. And then we're going to differentiate. What's the derivative of the area? It's the derivative of area with respect to time. And we are differentiating with respect to time. That is most of the time what we are doing. Sometimes people try to make up problems where it's not time, but usually it's time when it's related rates. On the other side, the derivative of pi r squared is pi times the derivative of r squared is 2 times my stuff times the derivative of my stuff. And then the fourth and final step is to plug in and solve. I'm going to plug in, what do I got here? I've got, well, actually, what have I got? So I'm trying to find this. So I should be able to plug in for everything except for the thing I'm trying to solve for. So dA dt, I should be able to get everything else. So I've got my 2 pi here. The radius is 50 centimeters. Dr dt, the rate of change of the radius, is 0.01 centimeters per minute. Now, I didn't write the units, but I think we can see that I'm going to have centimeters times centimeters per minute, which is going to be centimeters squared per minute, which makes sense for a rate of change of an area. I expect that area is changing. So let's see. So I've got 2 times 50, which is 100, times 1/100th, right? 0.01 is not 1/10, it's 1/100th. So I've got 100 times 1/100th is going to give me 1 pi. It's going to be pi. I just said the units, but I forgot the word. So here's the thing. I'm not really thinking about it being centimeters times centimeters per minute. I'm thinking, I know at the end that I have an area that's changing. So I should use units that are area, centimeters squared, per unit of time was minute. And I really want to emphasize that this is how I think about it, right? If I know it's a length changing, it should be my unit of length, so centimeters per time per minute. If it's area, it's centimeters squared per time. If it's volume, it's centimeters cubed per time. So you should always think about at the end, if you're trying to figure out what your units are, you should ask yourself, do I have a length, an area, or a volume? If it's length, it's whatever your unit of length is. It might be centimeters, it might be meters, it might be feet, it might be miles. But it's always just that to the first per unit of time. So it can be miles per hour. And if I talk about how an area was changing, it could be miles squared per hour, which sounds weird because usually you think of miles per hour as like how fast a car is driving.
I just have a quick question about the derivative of pi r squared. I kind of thought pi was a constant, and so you could use the. Okay, so for the derivative, is it? Oh, the constant times the. Okay, just saying it out loud made more sense.
Cool.
At first, I thought it was a product rule, but I realized, oh yeah,
constant. Well, so I do want to point out you're not wrong to think it could be a product rule, William. And I know William kind of worked through his thoughts there and made it make sense. But just so everybody kind of knows what's happening, when you take the derivative of a constant times a function, one way to imagine it is the constant just sticks around. Right? We have this constant multiple rule that says when you have a constant times a function, you take the derivative, you get the constant times the derivative of the function. But really, that's actually another way to think of that is actually that it's coming from the product rule. So if I take the derivative of pi r squared with respect to time, I can think of it as the product pi times r squared. And so when I do a product rule, it's the derivative of the first thing. So it's the derivative of pi times the second thing plus the first thing times the derivative of the second thing. So I get the derivative of pi times r squared plus pi times the derivative of r squared. But now, what's the derivative of a constant? Everybody.
0.
Thank you. 0 times r squared plus pi times the derivative of r squared, which we already know is 2r dr dt. So this rule, this constant multiple rule, really is, in some sense, coming from the product rule. It's just that the first half of the product rule is 0. So the other part of the product rule is, oh yeah, you've got the not derivative of the constant times the derivative of the function. But then we just usually remember it as, oh yeah, the constant just hangs out, is how I always say it. Yeah. Yeah, all right. Let's do some more. So let's see, where'd that question go? Sure. So someone, I don't remember the exact number, so I'm going to make up numbers. Somebody asked a question that was kind of similar to the following. I'm going to say it this way. A cylinder is expanding, has a radius that is increasing. At, let's say, I don't know, some ludicrous number like 2 meters per hour. It's getting very big, right? It's some, maybe I'm trying to think of like a shape of physical construction that would actually have an expanding cylinder, but I'm sure it's something that could be possible. Maybe it's inflating. Yeah, sure. You've got a weird pool and you're inflating it and it's just having a radius that's getting larger and larger and larger. Well, the height's still the same. It's not totally wacky. And we are filling it with water at a rate of, let's say, 15 cubic meters per hour. How fast is the water level changing when the cylinder is 3 meters deep? And I guess I should say how tall the cylinder is, because otherwise it doesn't really matter. Let's say a cylinder that is, let's say it's 10 meters tall. It's a giant, weirdly shaped inflatable pool. Are there questions about the setup before we get going here? I know I just kind of made this up. It's a little bit strange, but I think so. I've got a very tall cylinder like this. The height is not changing, but it is expanding in radius and it's being filled with water. And we're asking how the depth or height of the water level, how it's changing at a certain moment. All right. Here's our cylinder. The radius is changing, right? It's going like, boop, it's getting, and then we're filling it with water, which I should have saved the blue for the water. Oh well, because the water will be red. Someone injured themselves, had a bad day in the pool. The water is red. We want to know what's happening with the height. Yeah, and hopefully I'm filling it fast enough that it's actually filling up. Yeah. So let's identify what's changing. And I kind of feel like I need the other side of the board. So I'm going to have to go back and forth. So, what's changing? Pretty much everything, right? The radius is definitely changing. The volume is definitely changing. And although the height of the cylinder isn't changing, the height of the water is changing. So the height is also something that's changing. Okay. We know some of these things. We want to know other things. So we know how the radius is changing, right? The radius is increasing at 2 meters per hour. Which seems pretty reasonable. If you ever blown up a pool on your own, it can take forever. The volume, we're filling this thing with water at a rate of 15 cubic meters per hour. And finally, the height of the water, or the water level, if you want to call it that, that's the rate of change that we don't know. And so it's interesting to think, right? If we expanded it too quickly or more fast than we were putting water in, the water level actually might decrease. Okay, that seems weird but possible. I'm kind of curious about if that could actually happen with the way we've got it set up, but okay. We'll worry about that later. So then we need the equation relating the radius, the volume, and the height. Of course, for a cylinder, that equation is volume equal to pi r squared times h. I don't remember if it was this class or another class where someone was asking me, they were doing a cylinder and like it was a cylinder where the radius wasn't changing, the radius was known, and they just plugged in like the radius was 8. And then they're like, oh yeah, the volume is then 64 pi h, because if your radius isn't changing, this really isn't variable. It is in this problem because we made it weird. So that is the thing, that is the equation relating the non-time variables that are changing. And now we're going to differentiate now. This one is a little bit strange. I always find this one strange where you don't like solve, you don't plug in for one of these things, you're plugging in for the other. We have no way of relating R and H, unlike in a cone where we're like, oh yeah, the radius is just 1/3 the height, so we plug that in for the height. It's not the case here. Sorry, plugging for the radius, not the height. Anyway, here we're just going to use the product rule. And we differentiate. So the derivative of volume is dv dt. And oh yeah, I see. Okay. And for here, I'm just going to think of the pi as being a constant multiple. And the derivative of this product is going to be, well, the derivative of r squared is 2r times dr dt. And then I have to multiply by the h. Plus, now we leave the r squared alone. And the derivative of height is dh dt. So again, we have a constant multiple. It just hangs out in front. And the derivative of the r squared h is this product rule result here. We could maybe try to simplify that. I don't think it really makes sense to simplify it until after you've plugged in what you know and what you want to know, or try to solve what you want to know. So I know that dv dt is 15. I got a pi there. Ooh, do I know what the radius is? Do I need more information? Yeah, I probably need it. So I probably do need one more piece of information, because I asked how the water level is changing when the cylinder is 3 meters full of water, 3 meters deep. But I didn't identify how big the radius was, and that actually does matter. So when the cylinder is 3 meters deep, full of water, I feel like the language here is kind of terrible. When you make up questions. And the radius of the cylinder is, let's say it's 7 meters, just to pick a truly terrible number, I'm sure. Okay. So, got 2 times 7 meters times dr dt is 2 meters per hour. I'm just going to write the 2 times h, which is going to be if the radius of the cylinder was constant, the dr dt would be 0, but the radius is not constant in this problem, Sarah. Just want to make sure that's clear. Right, the radius is increasing. But yeah, so to point out, like if you had a problem where the radius was just like 8 meters the whole time, then you wouldn't even use the product rule. You would just say, oh, my volume is pi times 8 squared times h. So my volume is 64 pi h. And then you would just differentiate without using the product rule. Your derivative would be 64 pi times dh dt. So I get, let's see, 2 times 7 times 2 times h, which was 3 meters, plus r squared. R is again 7 times dh dt. All right, that's looking pretty hideous. And I want to solve for that. So we can divide by pi and then subtract, or we can distribute the pi and then, I don't know, it seems terrible either way, really. I do want to point out the units make sense. So I haven't written them, but I do want to say what they are. So right here, this is meters cubed per hour. Right here I have 2 times r, which is in meters, dr dt, which is in meters per hour, and height, which is in meters. This is meters, meters per hour, meters, which is meters cubed per hour. And then here I have meters squared times dh dt, which is going to end up being in meters per hour. Right, so meters cubed per hour should equal meters cubed per hour plus meters cubed per hour. Okay. So solving the rest of this is not my idea of a good time, but fine. Let's distribute the pi. So 15 equals, let's see, 2 times 7. Let's do the 7 last. 3 times 2 is 6. 6 times 7 is 42. 42 times 2 is 84. It's going to be 84 pi plus pi 49 pi dh dt. Subtract. So 15 minus 84 pi, and then divide by 49 pi. And that's meters per hour. And I do want to say this number is negative, right? If we calculate this, we get, 84 pi is way bigger than 15. 15 minus 84 pi. It's negative 248 approximately, divided by 49 pi. You get about negative 16. So what's happening here is the height is decreasing at 16 meters per hour at this particular moment, which again makes sense because the radius is kind of so large that even though we're filling it with water, it's expanding faster than the water is able to bring it up. So hopefully that makes some level of sense. And this is kind of a strange problem, but it works. Do another one. I'm a fan of really great problems, and I've got kind of a classic problem that I came up with years ago. I think now I'm like, did I come up with this problem? I either came up with this problem or a friend of mine came up with it, and it's a good problem. Yeah, problem that feels moderately plausible. Okay, here's what we got. Coffee. Liquid of the gods. Coffee is draining from a conical filter at a rate of a conical filter, which has, so it's shape of a cone, right? Point down. Almost always, if you got like volume in a cone, usually it's point down. Unless someone has specified otherwise. Certainly a conical, right? Hopefully you guys know what it looks like. Coffee grains, right? It looks like this and goes back. All right. So drain from a conical filter. This filter has a radius of 4 inches and a height of 8 inches. But it's kind of big. I've seen bigger, right? There's some pretty big industrial sized coffee makers that have some giant filters. And it's draining at 10 cubic inches per minute. Question 1. Sorry, I keep losing my spot on this page here. It's hard to see. Oh, sorry. Draining into a cylindrical pot. It also has a radius of 4 inches and a height of 8 inches. So now for the questions. Question 1. How fast is the liquid level in the filter changing when it is, what have I got here? 2 inches deep. All right, let's draw a picture. I long for board space. So here's my picture. Got my cone, and it's dripping coffee. Wow, that's my drops there. That's all right. Dripping coffee into the cylindrical pot. Okay, the cylindrical pot. And we have the coffee, the liquid level like that. We're going to call that, and we've got some, we'll have something down here as well. All right, so in the first question, we're given that, oh, and I should label the radius and the height. I was forgetting something. So the radius of this is 4 inches, and the height is 8 inches. And so the question, so back up, James. Process. What's changing? Volume is changing. Height of the water is changing. Also known as the liquid level. The radius of the surface is also changing, but I'm really not interested. I typically, so when I ask myself what's changing, I'm really more asking the question, what have they told me is changing? And what do I want to know is changing? And I kind of am blind to everything else, right? I know there's lots of other things about this liquid in the cone that is changing, right? Its volume is changing, its radius is changing, its surface area, right? I mean, there's a whole slew of things we could talk about that we're not going to talk about. They told me how the volume's changing. I want to know how the height's changing. Those are the things that matter to me. And they said that the volume was, let's see, whoops. It's coffee is draining from a concrete filter at 10 cubic inches per minute. So dV/dt should be what? Oh, sorry, grab my pen tip.
Ten inches cubed per minute.
All right, 10 cubic inches per minute. Well, we'll come back to that in a bit. And then we're looking to figure out what that is. All right, so second part, get the equation. The equation is going to be the equation for the volume of a cone, which is 1/3 pi r squared h. Yes, the volume of, so it's interesting that this cone is exactly 1/3 the volume of this cylinder, assuming that, right, I've drawn them so they look the same, right? This has a radius of 4 inches and a height of 8. This has a radius of 4 and a height of 8. So cone and cylinder that have the same radius and height, the cone is 1/3 the volume. And then we don't differentiate yet. So unlike the previous problem, which I've already erased, so I can't keep referring back to it, we're not going to use the product rule here. Right? I don't know what dr/dt is. I don't know how the radius is changing, although we could actually figure out if we want to. But what I would rather do is use the fact that in this cone, the radius is half the height. And that's true for any cone in this particular cone, meaning any smaller similar cone has a radius that's half the height. So I can straight away say radius is half the height. If you don't like doing it that way, meaning like just kind of saying what it is, you can also use similar triangles, right? The similar triangles here, I'm going to draw this down here. Here's my radius of 4 inches. And here's my radius of r. Here's my height, which is h. And here is my height, which is 8. So I can say, oh yeah, r is to h, right? This side is to that side as 4 is to 8. Or I can multiply both sides by h and say r equals 1/2 h. But I really just like to look at the big cone and say, oh, in the big cone, the radius is half the height. So in any cone, the radius is half the height. Always works. And then we plug that in with our radius. So I can say, oh, really? The volume is 1/3 pi times the height divided by 2 squared times the height, which of course I'm going to simplify before I differentiate. I'm going to get, let's see, this is h squared over 4, h squared times h is h cubed, so I end up getting that the volume is, let's see, 1/3 times a 1/4 is going to be a 1/12 pi. H squared times H is H cubed. Definitely worthwhile to simplify before we differentiate. And then step 3, we differentiate both sides. Derivative of volume is the derivative of volume. The derivative of 1/12 pi times H cubed is the constant multiple hangs out. And the derivative of H cubed is 3 times H squared times dH dt. And then we plug in what we know, solve for what we don't. I don't want to erase any of my pictures yet. I guess I can erase this picture, fine. So, plugging in for what I know, dV dt is 10. And I know that H is, what is H? H is, how fast is the liquid level changing when it is 2 inches deep. So H is, I guess I can write it here. So, we say that dV dt equals pi over 12 H squared dH dt. I think I missed a 3 there. I sure did. There was a 3 there. And then we said 10 equals pi. Well, let's cancel a 3 here and a 3 here and get a 4. H is 2, so I get 2 squared times dH dt. The 4's cancel. I should say the 2 squared and the 4 cancels. Divide both sides by pi, so that dH dt equals 10 divided by pi. 10 divided by pi, my unit should be, well, since I'm talking about how a height or a length is changing, it should be single unit of measurement, meaning inches in this case. Not inches squared for area, not inches cubed for volume, but just inches per minute. Now I want to talk about why my answer is just a tiny bit wrong. Or depending how I write the answer, it's wrong. If I just said dH dt is 10 over pi inches per minute, that's wrong. Because that's saying that my height is increasing at 10 over pi inches per minute. But I know that the height of my water is decreasing. So I could use words and write dH dt is decreasing, or I should say the height is decreasing at 10 over pi inches per minute. Right? I could write out the words. Or I could instead say, really, I should have started with dV dt is negative because the volume is actually decreasing. So it's got a negative rate of change, which is just going to change the sign of my final answer. So that negative 10 equals all that, and dH dt is negative 10 over pi inches per minute, which makes sense. So I could say that, the height, dH dt is just a negative number, meaning the height is decreasing, or I could write out in words and say the height is decreasing at 10 over pi inches per minute. But you somehow have to indicate that you know that it's lessening, not increasing. And I should say more broadly, if something is getting smaller, we know its rate of change, aka its derivative, should be negative. Something is getting larger, its derivative should be positive. Okay, but then the second part of this question. And the second part of this question is, how fast is the volume in the cylinder increasing? So, here's my cylinder again. So, when the depth of coffee is 2 inches in the pot, or I could say that more like a normal person, when the coffee in the pot is 2 inches deep, how fast is the height of the coffee, or the depth of the coffee, or the liquid level increasing? I should really say changing to not give away that it's increasing. Right, you'll definitely see people write in these related rates questions asking how something is changing to not give away whether it's changing in a positive or a negative way. But you should definitely think about, what's happening in this problem? Is the thing I'm talking about increasing or decreasing? So let me ask you guys, if we're talking about Now the liquid level in the pot of coffee, should that liquid level be a positive change or a negative rate of change if it's getting higher and higher? Yeah, right, definitely, right? DHDT, whatever that ends up being, should be positive because it is definitely getting higher. Okay. And I shouldn't have labeled this 2 inches yet because that's just the moment of time. Really, we're calling this H, we're calling this R. And so now, still the same sort of setup. We still know that dV/dt is 10, and this time it is positive 10. Because although this is losing volume at 10 cubic inches per minute, this is gaining that volume at 10 cubic inches per minute. And we are interested in what dH/dt is. All right, so now part 2, the volume equation relating them, meaning in this case the volume of a cylinder, so it'd be volume equal to pi r squared times h. And now I've definitely seen people make an error here in that they want to use the same relationship for r as they did before. They want to say, oh, r is 1/2 the height, whatever. It's super easy if you've got a cylinder. The radius is 4 inches, no matter how high the water is, because we're in the cylinder, not in the cone. So here we can just say, oh, the volume is just 4 squared is 16. The volume is just 16 pi times h. And now if I take the derivative of both sides, I get dV/dt equal to 16 pi times dH/dt. So I only have one thing. Well, that's not true. I have 2 things I know, but there's only one place to plug any of them in. I know the dV/dt is 10. There is nowhere to plug in the fact that it's 2 inches deep. That's okay. Sometimes they give you too much information, they're trying to trick you. So I'm going to plug in, I'm going to get 10 cubic inches per minute, if you really want to write the units, equal to 16 pi times dH/dt. Now I should point out, this 16 pi is hiding in inches squared, right? When I plugged in 4 for the radius, I was really plugging in 4 inches. And 4 inches quantity squared is 16 inches squared. So this is really 16 pi inches squared. So then when I divide both sides by 16 pi, 2 of the inches cancel out, and I just get inches per minute. So my final answer here is dH/dt equals 10 over 16 pi is going to reduce to 5 over 8 pi inches per minute. And it doesn't matter how full it is, right? Whether it's just barely full or super full, the depth of the water level is still going to be increasing at the same rate because it's not like going into a wider thing at the top or a narrower thing at the top. So this is an example of a problem where it doesn't actually matter what height the water level is at in the second part here. You get the same answer no matter, right? I could have said the coffee is 7 inches deep and there's still nowhere to put the 7. Questions about this? Okay. Oh, there's a question. Yes, to the person writing, you may be excused, but just to everybody, in case, so I posted an announcement Sunday last week that said the quiz was completely optional this week. Everybody got credit for the quiz already. So if you're worried about not having in the quiz, don't worry about it. Everybody got credit. Yes, if you need to go, please feel free to go. All right, so let's see here. I've got one more related rates problem that I definitely want to do, and then we'll see how everybody feels after that. We'll take a break probably after that. So, yes. Right. I was going to say myself, but I'm not quite as tall as the person who needs to be in this problem. So a 6 foot tall, not James person walks away from, I forgot the numbers that made this turn out especially nice. I'm just going to make something up that's probably not going to be as nice. From a, sure. I want to pick a nice number now, but okay. From a 14-foot tall street lamp. How fast does the length of the shadow cast by the lamp change? Oh, I need to say how fast he's walking, sorry. A 6 foot tall person walks away from a 14-foot tall street lamp at a pace at 4 feet per second. How fast does the length of the shadow cast by the lamp change when the person is 10 feet from the base of the lamp? So let's draw ourselves a picture. Part of me just wants to not write out the question, but I kind of feel like it's important to write the question so we can refer back to it. So let's draw a picture. We got a street lamp, the ground, emitting light. And then here's a person who is 2 inches taller than James. Maybe an inch and a half on a good day. So we're casting a shadow and we're walking away from the lamp. So really important here in a situation like this, you have to label the things that are changing with variables. So this length here, the length between my person who's not me and the street lamp, the base of the street lamp, that's changing. I'm going to call it X. And then the length of my shadow, or not me person, shadow, is also changing. All right. And now let's identify. So what's changing? X and S. X is changing. I know that dx dt. So dx dt is how the distance between me and the lamp is increasing or changing. It's the same as how fast I'm walking. Sorry, I can't say not me anymore. It's just me. It's me on a really tall day wearing heels or something. So dx dt, the rate of change of the distance between me and some stationary object, is how fast I'm walking. It's 4 feet per second. So if you know how fast something is going, you just have to write it as how some distance between that thing and a stationary thing is changing. And then I want to know how fast the length of the shadow is changing. And it definitely seems like, right, if we walk further away from the lamp, the shadow should be longer, right? If we're standing over here, the lamp's going to cast a longer shadow because there's a smaller angle. Okay, we need an equation relating the non-time variables. This is another situation where similar triangles are coming into play. Because really, the picture I have here is similar triangles. Big triangle has, oh, I forgot to label that, sorry. I forgot to label all the things. This lamp is 14 feet high, that's not changing. this person in heels is 6 feet tall. All right, so big triangle, the height is 14, the base is x plus s. So I can say in the big triangle, 14, I should write it over here then. 14 over x plus s, the ratio of the height to the base, is equal to, in the little triangle, height to base is 6 over s. Now maybe I didn't set this up in the most normal way. Doesn't really matter. We're going to cross multiply regardless. So cross multiply, you get 14 times s equals 6 times x plus s. And then we can distribute. You get 14s equals 6x plus 6s. And then I can subtract 6s and get 8s equals 6x. That's pretty easy. I mean, you could even divide both sides by 8 or 6, depending on what you felt like. But it's easy enough at this point. So now we're going to differentiate both sides. The derivative of 8s is 8 times ds dt. The derivative of 6x is 6 times dx dt. Sorry, my picture is in the way here. Okay, we know what dx dt is, and we're being asked, if you recall, how fast does the length of the shadow cast out of the lamp change when the person is 10 feet from the base of the lamp? Well, one of the reasons I want to do this problem is because much like the problem we just did before, it doesn't matter how far the person is from the lamp. Just like it didn't matter how full the pot of coffee was. In this case, we only know that dx dt, or dx dt is the only thing we can plug in for. That was 4. So we have 8 times ds dt equals 6 times 4 feet per second if you want. And then divide both sides by 8. So you get ds dt is equal to 24 divided by 8 is 3 feet per second. So it's kind of interesting here that it doesn't actually matter how far the person is from the lamp. It just matters how tall they are. It matters how fast they are walking and the ratio between their height and the lamp's height. Those are the only things that really play a role here. But the person could be 10 feet from the lamp, or assuming that the lamp could cast a shadow, like it doesn't matter how far you are from the lamp, they could be 100 feet from the lamp. And as long as they are walking at 4 feet per second, the length of their shadow is increasing at 3 feet per second. That's kind of it. Kind of neat. Sometimes people will ask this question in a slightly different way. Sometimes people will ask instead, so I always like to think about how fast the length of the shadow is increasing, right? So I'm measuring the shadow from my foot to the end of the shadow. However, some people like to say, how fast is the tip of the shadow moving? And there's a difference in that question, right? When they say the length of the shadow, the reference point is kind of my foot, my feet. Whereas when asked how fast the tip of the shadow is moving, that should be compared to some stationary reference point. So I'm really asking how fast this point is changing compared to being far away from this only stationary thing we've got. So what I'm really asking for in that question is not what ds dt is, but how fast this entire length is changing. Well, it's really not hard to answer if you've already done this part. In fact, you can literally just add the answers together. If I'm walking at 4 feet per second and my shadow is increasing in length at 3 feet per second, then the tip of the shadow is moving at 4 plus 3 equals 7 feet per second. More mathematically speaking, I'm asking, how is x plus s changing? So I'm really asking for what's the derivative of x plus s? Well, that's easy. That's just dx dt plus ds dt, which we've already found. So if I was to ask the problem this way, I would still answer the other question first. Meaning, if someone said, how fast is the tip of the shadow moving? I would say, well, really, I'm just going to answer how fast is the length of the shadow changing, and then add that to how fast I'm walking. Because that's what we get. We get how fast we're walking plus how fast the shadow is increasing. It's going to be 4 plus 3, which is 7. It's kind of neat. Most problems we deal with that are related rates problems, we typically actually need to know like the moment when the person is 10 feet from the lamp or the water is 4 feet deep or whatever. But there are a few problems where you actually don't need that other piece of information to add. When I say, or when anyone says, or when you read the word linearization, all you should really think is, I'm finding the equation of the tangent line. So let me show you a picture that I drew while I was taking a moment. So here's the idea behind a linearization. And hopefully you can read what I've written, but I'll spell it out too. So here's a function f. F is differentiable and continuous. And I'm really interested in figuring out what f of x is. I want to find the function evaluated at some place that's not particularly convenient. So what we do, I forgot to modify one thing. Hopefully I'm going to do one thing that might make it easier to see what's on my screen. Yeah, I've adjusted for the light, but hopefully that makes it slightly easier to see what's on my board there. So I want to know what f of x is, but f of x is hard to figure out. So instead what I do, say, well, a is super easy to evaluate this function at. And I'm going to say, instead of trying to find f of x, I'm going to figure out the equation of this tangent line, and then plug x into this linear function, which is easy to evaluate, and figure out what L of x is, the linearization of x. So the whole idea is find the equation of the tangent line and use that tangent line, that linearization, so that I can approximate the value of x in the function by L of x instead of whatever f of x is. And the difference, as long as x and a aren't too far apart, the difference is pretty negligible. So here's how we do it. And this is stuff you guys already know. You might just not know that you know it. So the function is f, or f of x, if you want to call it that. And here's how we find the equation of the tangent line. Here's how we find the equation of a line through a point. Point slope form. Y minus y1 equals the slope times x minus x1. But I'm going to change the names of things just a bit. Instead of calling the point here, and this is the point I'm finding the tangent line at, instead of calling that point x1, y1, I'm going to change the name to a comma f of a. x1 is the a value. y1 is the function evaluated at that a value. And instead of calling the slope m, well, we know that we can find the slope of a tangent line by finding the derivative at the point of tangency. Well, the derivative there is f prime evaluated at the point A. So, which I've already written here, our m is f prime of A. So rewriting this, just using new names, I have y minus f of A equals f prime of A times x minus A. M is f prime of A, x1 is A, y1 is f of A. And then finally, we isolate y and say y is equal to f of A plus f prime of A times x minus A. And typically, instead of writing y here, we use the notation capital L of x for the linearization of the function. It's equal to f of a plus f prime of a times x minus a. So that's the idea very generally, but I really, really want to impart to you that all a linearization is the equation of the tangent line at a certain point. So let me go back one sec. Sorry, one moment here. Grab one thing. Nope. Okay. So that's the whole idea. And we're going to do some problems with this. And we'll start off with some fairly standard examples. So one example is to say, now I should kind of. So we could find the linearization. It's just the equation of the tangent line. Find the linearization of, say, f of x equal to the cube root of x at the point x, sorry, I should say a really, at a equal to, typically it's going to be a value that is convenient to plug in, like something that you can easily take the cube root of, like 8, 27, or 125, or 64. Let's do it at 8. Now, you can either just memorize the formula. You say, okay, well, yeah, sure. L of x is f of a plus f prime of a times x minus a. We need to identify a few things. Well, in fact, they're already pretty much identified for us. A is 8. F of x is the cube root of x, or x to the 1/3. And f prime of x, just take the derivative, is 1/3 x to the negative 2/3. But I need to actually plug in the values. So f of a, or f of 8, is 8 to the 1/3. The cube root of 8 is just 2. And f prime of 8 is 1/3 times 8 to the negative 2/3, which is going to be, let's see, 8 to the negative 2/3 is 8 to the 1/3 to the negative second. So it's going to be 1/3, 8 to the 1/3 to the negative second. 8 to the 1/3 is also 2, just like 8 to the 1/3 was 2. And so that's going to be 2 to the negative second, which is 1 over 2 squared, which is 1/4. So it's going to be 1/3 times 1/4, which is 1/12. So here's what we're saying. We're saying for this function at the point 8, 2, the slope of the tangent line is 1/12. And the, well, that's really, and the, I guess the y value is 2. We could graph it if we wanted to. I know that the cube root of x looks something like this. And I'm over here at the point 8, 2. My tangent line looks vaguely like that. And it's got a slope of f prime of 2, which is 1/12. So now the equation of that tangent line, my linearization is this. It's L of x equals the y value, which is 2, plus the slope, 1/12 times x minus 2. That's the equation of that line. And you can see, hopefully you can see, that as long as we're pretty close to that point, the y values of this line and the y values of the function are close to each other. But if we get really far away, right, like over here, the y value of the line and the y value of the function are very different. So what we can do is we can use this linearization to approximate values of this function for values of x that are close to where we linearized it at. So I could say, I'm gonna erase my picture here. I could ask you to use this linearization to now approximate the cube root of 9, which I don't know, but I can plug it in and say, well, the cube root of 9 is approximately this linearization evaluated at 9, which is going to be equal to, I'm just plugging in 9 for x here. So,
is that x minus, is it supposed to be x
yeah,
minus
so
8?
I made a mistake. Like, let me actually go through it and point out the mistake, but I feel like most people are seeing already. But let me show you the mistake. So I'm going to get 2 plus 1/12 times 9 minus 2. And I'm like, that seems kind of wrong, especially if I actually go through with it. Right? I get 2 plus 7/12. I feel like the cube root of 9 shouldn't be more than 2.5, right? If you look at a calculator, the cube root of 9 is definitely not 2 plus 7/12. The cube root of 9 is 9 to the 1/3. About 2.08. And where we made the mistake, where I made the mistake, was making the mistake of putting a 2 in here, right? So this should be x minus a, not x minus f of a. So that shouldn't be 2. That should have been, x makes it look funny. That should have been 8. Where's my eraser? And we knew we were making a mistake when we, at least I knew I was making a mistake when I was saying, oh, 9 minus 2, those should be close to each other. But 9 and 2 aren't that close in the world of this particular problem. It should have been 9 minus 8. Those are much closer. So we're getting 2 plus 1/12, which is, I would probably write my answer as 25/12, right? 2 is 24/12 plus 1/12 is 25/12. And if you use a calculator, 25/12 is, oops, that's not right. 25 divided by 12 is 2.083333, whereas the cube root of 9 is 2.08 something. It's 2.08008. So, I mean, our estimate is correct to the 100th place, which is pretty good. I want to also show you with this picture what's kind of, even more what's happening here. Just kind of go back to the picture we had. What's really happening is, there's my tangent line. Here's point 8, comma 2. And what I'm doing over here at 9 is, instead of finding the y value for the function, which will be right there, I'm saying instead I'm going to use this y value, which is 2 plus the rise of that line, right? Essentially, I'm doing 2 plus the rise, where the rise is, well, I know that rise over run is equal to the slope. So the rise is equal to the slope times the run, or the slope, 1/12, times the run, which is how much change in x there is, which is 9 minus 8. So that's really what we're doing. We're taking the y value that we kind of already know is good and adding a little bit on. How much on? How much the rise is from here to there. All right. So let's look at some more questions. So I personally am a fan of the question of the style, use a linearization to estimate this thing. For example, I could say, use a linearization to estimate the natural log of 1.07, which does not feel very straightforward because you're not really given any of the things. So in a problem like this, it's our job to identify what the function is and to also identify the convenient value that's going to play the role of A. The function is almost always just the thing you've got, except replace the number they've given you with x. So our function is the natural log of x. I'm just taking my 1.07 and replacing it with x. And we might as well write down the derivative because we know we're going to need it. The derivative of our function is 1 over x. Our other job, kind of the hardest part usually-ish, is identifying what's A. A should be a value that's close to what we're trying to plug in, that is easy to plug in. Okay, what's a number that's close to 1.07 that's easy to take the natural log of?
1.
Right. There's only one answer, and it's 1. Because the natural log of 1 is 0. So f of a is the natural log of 1, which is 0. And f prime of a is 1 over 1, which is 1. So it's always our job to figure out what value of a we're trying to throw into our function, where a should be easy to evaluate. So now we write the linearization. And I do think it's worth memorizing, but if you ever forget, you can always be like, okay, linearization, y minus y1 equals the slope times x minus x1. My slope, so then I've got y minus, there's my y value, 0, equal to my slope, 1, times x minus my x value, which also happens to be 1. So in this case, L of x is just x minus 1. You could also write it up that way. You could say, oh yeah, L of x is f of a plus f prime of a times x minus a. F of a is 0, f prime of a is 1, and a is also 1. Graphically, this does make sense. The natural log function looks like this, and the tangent line exactly is the line y equals x minus 1. So then we're trying to figure out what's happening at, or what natural log 1.07 is. So natural log of 1.07 is approximately the linearization at 1.07, which is 1.07 minus 1, which is just 0.07. And it is kind of interesting that for values of x near 1, the natural log of those values is just the value minus 1. And if you plug into a calculator, the natural log of 1.07 or 1.0, take your pick, something that's not too much different than 1, the natural log of 1.07 is 0.06765. So pretty close to 0.07. Not too shabby. There was something else I wanted to point out. Yeah. There's 2 more problems I want to do of this nature, and then we'll look at a few other things that are a little bit more geometric, maybe is the right word to say. At least 2 more, unless you guys really want me to do more. So, yeah, let's do this one. So use a linearization to estimate. I like roots. I feel like roots are kind of the ones that seem the most interesting. I want to estimate the square root of 95. All right, so our function is the square root of x, or preferably x to the 1/2. We know we need the derivative. X prime of x is 1/2 x to the negative 1/2, or if you prefer, 1 over 2 root x. And now we have to decide what's our a value. What's the closest number to 95 that we can plug in and easily take the square root? Well, it's going to be a square number. So our job really is to think of all the square numbers and then find the one that's closest to 95. And yeah, and this one, usually the people will try to make it kind of obvious. But if you're not sure, you can be like, okay, well, let's see. 8 squared is 64. 9 squared is 81. 10 squared is 100. 100's closer. Now, if you are kind of if you're more in the middle, it can be kind of dicey. Like I've definitely asked people before to estimate like the square root of 42, and they're like, 42. 36 is 6 away. 49 is 7 away. I guess I should use 36, but it doesn't feel like a great choice. So just make sure that you're using the thing that's closer that is still easy to plug in. Usually they'll pick something that's pretty close to a number that's actually easy to deal with. So yeah, our a value should be 100. Our f of a is the square root of 100, which is 10. And our f prime of a is 1/2 100 to the negative 1/2. 100 to the negative 1/2 is 1/10. That's why I like to write it this way better. I would really much rather write this as 1/2 square root of 100. That's easily 1/2 times 10, which is 1/20. So then, by the way, should our answer be bigger than 10 or less than 10?
Less than?
Right. Taking the square root of 95, it definitely is less than the square root of 100, which is less than 10. So our linearization is f of a plus f prime of a times x minus a. Or as I'm really kind of thinking about it in my head, y minus y1 equals the slope times x minus x1. The reason I say this, and the reason I'm kind of mentioning it over and over again, is I've seen many people over the years mix up the plus and the minus sign here. Say that this is a minus and this is a plus, or they're both plus, or they're both minus. But if you remember that it's the slope of the tangent line, if you're not sure where the pluses and minuses go, you can always work backwards and be like, oh, well, I know it's y minus the y value equals the slope times x minus the x value. That always works for me. So then this is going to be f of a, which is not 100. F of a is 10, plus f prime of a, which is 1/20 times x minus a, and a is 100. When you're doing this, your answer should make sense, right? I should get an answer that's close to 10 because I'm taking the square root of something that's close to 100. It should be 10. It shouldn't be minus something, right? It should be 10, but not minus a whole lot, right? This 1/20 assures that it's not going to be too much I'm subtracting off. And it is going to be subtracting something off because I'm going to put a 95 in there and get a negative number there. So let's see what I get. I get that the square root of 95, and I really like to write that the square root of whatever is approximately equal to the linearization at that value. It's going to be 10 plus 1/20 times 95 minus 100. 95 minus 100 is negative 5, so it's 10 minus 5/20, which is 10 minus 1/4. And you could either, if it's an easy fraction to change to a decimal, I would, and say, oh, 10 minus 0.25 is 9.75. Or you could write it as a fraction and say it's 40/40 minus 1/40, which is 39/40. Not 40ths. It's 40/4 minus 1/4, which is 39/4. And just to compare, the square root of 95 via calculator is, I always forget this happens. Square root of 95, super helpful. It's the square root of 95. Geez, calculator, thank you. I really appreciate all the help you give for me. It's approximately equal to 9.746. So pretty close. Okay, I'm going to do one more in this nature because there's one more type of problem that I have seen that can be somewhat challenging. And it really kind of just depends on how the person has decided to write the thing. So let's say I wanted to find, or I wanted to estimate the tangent of 46 degrees. 40, let's do 44 degrees. All right, so let's write down some stuff. We know our function is tangent of x. We know the derivative is secant squared of x. And what is the value that I actually want to use? It is close to 44 degrees, but much easier to evaluate.
45.
Right. Exactly. So I'm going to use 45 degrees. I know that tangent of 45 degrees, which is my f of a, tangent of 45 degrees is 1. And my f prime of a, which is secant squared of 45 degrees, is going to be, I'm going to do 1 over cosine squared. 1 over cosine squared of 45 degrees. I know cosine of 45 is root 2 over 2. So I get 1 over root 2 over 2 squared, which is 1 over 2/4, which which is 4/2, which is 2. So secant squared of 45 is just 2. Secant of 45 is really just root 2, and then root 2 squared is 2. Okay, so here's what I'm going to make. Well, not quite yet. So my linearization is f of a plus f prime of a times x minus a. So that's going to be f of a, which is 1, plus f prime of a, which is 2, times x minus a, which is x minus 45. Okay. I'm already in the process of making a mistake, but I'm not going to point it out yet until we get to the place where it's actually really, really blatant that we've made a mistake. Don't worry, we're going to fix it. So now I'm going to use this to approximate tangent of 44 degrees. So tangent of 44 degrees is approximately the linearization of 44, which is 1 plus 2 times 44 minus 45. That's a negative 1. So I get 1 plus 2 times negative 1. That's 1 minus 2, which is negative 1. And now we have to kind of rely on our knowledge about trigonometry to kind of identify why this is a real problem. Tangent of 44 degrees, well, 44 degrees is really in the first quadrant. Tangent is really, really positive in the first quadrant. And moreover, I mean, the bigger kind of issue here is that tangent of 44 degrees should be pretty close to tangent of 45 degrees, right? If we use a calculator and we're in degrees, tangent of 44 degrees is about 0.965. Definitely not negative 1. The issue here is an issue of radians and degrees. And so I did kind of make an on-purpose mistake here, and that's I didn't write the degrees up here. 45 degrees there. And so when I do this subtraction, tangent of 44 degrees is the linearization at 44 degrees, which is 1 not in degrees plus 2 times 44 degrees minus 45 degrees, which is 1 plus 2 times negative 1 degree, which is 1 minus 2 degrees. But it's not 1 degree minus 2 degrees. It is 1 minus 2 degrees. The problem is degrees have kind of a dimension or unit, but radians don't. So the issue here is that we actually need to change this degree measurement to radians. I would still do the problem like this. I don't think you want to change, you definitely don't want to change 44 degrees to radians. That's terrible. What you want to do is you want to do it in the easiest units possible until the very end. And then the very end, you're like, oh, well, now I'm trying to put together things that have different units. I need them to have the same units or to not have units. And radians don't have units. Calculus works best in radians. So we're going to change this to, I'm going to write it up here because I want you guys to actually be able to see it. 1 minus, so how do I change degrees to radians? I multiply by pi radians over 180 degrees. The degree units cancel out. I can also cancel a 2 and get pi over 90. And I get 1 minus pi over 90. Or if you prefer a common denominator, 90 minus pi all over 90. Either way, if you use a calculator to actually see what that is approximately, you get 1 minus pi over 90 is about 0.96509, whereas tangent of 44 degrees was about 0.965. So they're actually, it's kind of cool. They're pretty close to each other, right? Sorry, I know you guys can see me. But like they're close to they're the same to the 1,000th decimal place. That's pretty good. Anyway, so that's something to be aware of when you're dealing with trig functions and degrees specifically, is that someone might ask you to estimate something in degrees and you should still like use the nice degree measurements, but at the end you're like, oh, if you're adding degree things to non-degree things, you really need to change the degree thing to radians. Okay, but then we might ask other questions. Questions that are less like the ones I am posing here.
I have a question.
Go ahead.
So if we want to double check our answers with using the calculator, should our mode be in degrees or radians?
So I put my method was in degrees there because I was doing tangent of 44 degrees.
Okay.
But I know someone else asked me a question, like they were asked to approximate something like, I don't remember exactly what it was. It was something like sine of pi over 6 plus 0.1. None of that's in degrees, by the way. In this case, you don't really have a huge issue here. I mean, it might have been 0.01, actually. So the idea here is still the same. We're going to find our function is sine of x. Our derivative is cosine of x. These never come out nice. Our a value is clearly pi over 6, right? Pi over 6 is close to pi over 6 plus 0.01, and it's nice to evaluate things at. We know that f of a, which is sine of pi over 6, is sine of pi over 6 is 1/2. And then f prime of a is cosine of pi over 6, which is root 3 over 2. So then using the linearization, and I know we don't have to write it out every time. I think it's worth writing out, at least until you really do know it. So our linearization is f of a plus f prime of a times x minus a. So that's going to be 1/2 plus not a lot, right? If we're taking the sine of something close to pi over 6, our answer should be close to what sine of pi over 6 is, which is 1/2. So whatever this is over here, it shouldn't be much. F prime of a is root 3 over 2. Already I'm feeling terrible about this. Actually, I think we're wrong just because the numbers aren't nice. And then x minus a is x minus, our a value is pi over 6. So then to approximate this, we're going to say that sine of pi over 6 plus 0.01 is approximately the linearization at that same value, pi over 6 plus 0.01, which is, I'm just plugging in the 0.06 plus, sorry, the pi over 6 plus 0.01 here. So meaning 1/2 plus root 3 over 2 times, I'm not going to write it all out. I'm just going to say it's pi over 6 plus 0.01 minus pi over 6, so it's just 0.01. And then you could simplify that. I mean, so here's what I simplify this. I get 1/2 plus 0.01 is 1/100th. So it's root 3 over 2 times 1 over 100. So that's going to be, I mean, I guess I can get a common denominator. 100 over 200 plus root 3 over 200. So it's 100 plus root 3 over 200. Clearly close to 1/2, right? 100 plus root 3 is like 101.7. Divided by 200 is still pretty dang close to 1/2. Via calculator, we get 100 plus root 3 divided by 200. It's about 0.5086. Or I should say 7. Whereas if you actually took, so here I'd have to change to radians if I'm going to take sine of that. So let me change my mode to radians. And then I'm going to take sine of pi over 6. Where'd you go, pi over 6 plus 0.01. And we get 0.5086. So pretty close. Again, right, your answers should be pretty close. If they're not, it means you should go back and check your work. So I want to point out here that we didn't have to do any degree to radian changing because the answer was already asked, or sorry, the question was asked in terms of radians, right? There wasn't a degree symbol. That means we're using radians. Okay. Then there's also some more like physical examples. Here's kind of straightforwardish one. Approximate how much f of x equal to x squared changes when x goes from 6 to 6.2. We could actually do this, right? We could actually calculate 6.2 squared minus 6 squared and see what the actual change is. But I want to approximate it because it's easier. So here's what I know. In fact, let me draw a picture again. So right, here's our parabola, y equals x squared. And we're trying to go from 6 to 6.2. I know that f of 6 is 36. I don't know what f of 6.2 is. I mean, I could square 6.2. It's not that hard, but I don't really want to. So instead, I'm going to use the tangent. And I'm going to say, well, this here, my rise, people also call this the differential. dy or df, kind of either way. And that's my dx. And we know that the derivative, df dx, and I will say this now, I'll say it a lot of times, this is not a fraction. However, it acts like a fraction in just about every way that matters. We treat it like a fraction all the time. It certainly has fractional interpretations, but I just should say it's not a fraction. It's a derivative, but we treat it like a fraction. So definitely it acts like a fraction. Here, df dx, the derivative at this point, so the derivative at x equal to 6 is, well, the derivative of x squared is 2x. At x equals to 6 is 12. That derivative is 12, meaning this line has a slope of 12, meaning if I move 1 over, I go up 12. If I go 0.2 over, I'm going to go up 12 times 0.2. So if the run, aka the dx, is 0.2, the rise, aka the dy, is 12 times 0.2. And the reason for that is really because of this. Rise over run is dy dx, which we just said was 12 for this particular part of the graph. So if I'm just trying to find the rise, I can say that the rise is equal to dy dx times dx, which is 12 times 0.2, which is going to be 2.4 in this case. So in this particular situation, the 12 times 0.2, or if you prefer, the f prime of a times x minus a, that's my df or my dy, either name is fine. And that's my differential that's approximating the change in y. If I go over 0.2 here, I'm going to go up about 2.4. How much exactly? Well, to do that, we actually have to do some more work. But I really want to point out, right, this question is asking for how much it changes, whereas previously I might have asked to approximate f of 6.2. So the difference is the change is just this much, right? This value minus this value, whereas that part there. Whereas if I was actually doing the whole linearization, I would do my f of a, which is 36 plus 2.4. So if I said, what is 6.2 squared approximately? It would be 36 plus 2.4, which is 38.4. To figure out what this difference actually is, so we look a little higher. Right there is actually 6.2 squared. Whereas over here, that's actually just my differential. So I guess I could do 6.2 squared if I really wanted to, but let's just do it calculate. 6.2 squared is 38.44. 38.44 minus 36 is 2. I didn't need why I'm using a calculator for that. 38.44 minus 36 is 2.44. So the actual difference, delta F, is 2.44. We approximated that with dF, the differential is 2.4. And they're pretty close. Good enough. Well, good enough depending on the situation, I guess.
Where'd you get 2x and 12?
So the 2x came from taking the derivative. Or my function was x squared, the derivative was 2x. And then I got the 12 because I said I really want to know what the derivative is at this point. And x is 6. And so I plugged in x equal to 6. And I got 2 times 6, which is 12.
Okay.
Yeah, so whenever you're talking about these kind of either differentials or linearizations, which are very related to each other, you're always looking at the derivative at a particular point. So here I was looking at the derivative of this x squared function at the point where x is 6. An example that sounds maybe better is the following. A sphere with a radius of 3 inches is coated with ice that is 1/4 of an inch thick. How much ice is there? Approximate the volume of ice. So we could find the actual volume, right? We could draw a picture here. Sure. Right, so we've got our sphere, and then it's coated with ice. And so, right, the volume of ice would just be the volume of the large sphere minus the volume of the small sphere. So that would be the change in volume, delta V. We use a capital delta for actual change. And that would be equal to, well, the volume of the big sphere is 4/3 pi times the big radius, which is 3.25 inches cubed, right? The volume of the sphere is 4/3 pi r cubed, minus the volume of the inner sphere, which is just the original sphere, which is 4/3 pi times 3 cubed. 3.25 cubed is definitely a calculator thing I would need to do. I'm not going to do that. I'm just going to tell you it's approximately 30.7 cubic inches. You can throw that in a calculator, you can throw that in a calculator, subtract, and you get that. The approximate volume difference, or I should say the approximate volume of the ice, which is the difference in the volumes between these two spheres, well, we can find the differential. Yeah, where am I? 30.7. Great. So here's what we know. dVdr is the derivative of the volume equation. The volume equation is 4/3 pi r cubed. This is one of my favorite mathematical facts, by the way. The derivative here is 4/3 pi times 3r squared, which is just 4 pi r squared. And I've always thought it was interesting that the derivative of the volume of a sphere is the surface area of the sphere, right? The surface area of the sphere is 4 pi r squared. It's kind of neat. It doesn't really come up anywhere else except for one place, that the derivative of the volume is equal to the surface area. It also is true for circles that the derivative of the area is equal to the circumference, right? The derivative of pi r squared is 2 pi r, which is the circumference. It doesn't work for any other shapes, but it does work for circles and spheres. That the derivative of one equation gives you the next lower dimensional equation. Kind of cool. Not particularly poignant, but cool. So then I'm going to solve for dv by multiplying both sides by dr. So that dv is equal to 4 pi r squared dr. And again, I really just want to point out that's my f prime of a. That's just my derivative. That's just my x minus a. Right? If I'm thinking about the linearization, this is just the change part, right? Right. So if I'm thinking of, right, v of x equals, I guess I could use v of a plus v prime of a times x minus a, right? If I was trying to approximate the volume of the larger thing, I would be doing it this way by saying, oh, it's the volume of the smaller thing, and then I'm approximating the difference in the volume. That's what this part is here. The approximate difference in the volume, if you like. Okay. Now, what's the radius I'm actually going to plug in to try and approximate this? Am I going to plug in 3 inches or 3.25 inches? Definitely the easier one. Always the easier one. So I'm going to say, okay, dv is going to be 4 pi times 3 inches squared. Right, just like in general, we pick the a value that is easier to plug in. And then I'm going to multiply by the difference in the radius. The larger radius was 3.25, the smaller radius was 3, the difference is 0.25. So I end up with 4 pi times 9 times 1/4 cubic inches. The 4's cancel. You get 9 pi cubic inches, which is 9 pi is about 28.3. So certainly not the same as 30.7, but not so far off that it's an unreasonable estimate of the amount of ice. So linearizations and differentials both kind of rely on this idea of using the tangent line, right? And right? And kind of the difference between them is when you're using a linearization, you're typically saying, what is the function equal to at this particular value? And you're doing the f of a plus f prime of a times x minus a. Whereas when you're using a differential, you're typically being asked to talk about just the change, right? So, yeah, let me write one more thing, actually. I can erase some of this, yeah. So, if we're talking about the linearization being f of a plus f prime of a times x minus a, another way to view this is that f prime of a is the derivative df dx. X minus a is the change in x dx. And then the product of these, well, the dx's cancel, and this is df or dy, the approximate change in the function value or the y value. Hopefully that helps clarify what's going on with this particular topic. It can be a little bit challenging. If you get stuck, go back to the place where you say, oh, I'm really just finding the equation of a tangent line. And maybe I'm finding the entire equation of the tangent line and doing f of a plus all this difference, or maybe I'm just being asked to find the difference. But really at some base level, that's what these are all about.